Hello, welcome for our Monday seminar. Actually, when I advertised the seminar last week, and I gave some characterization of one of the presentators, I said that Federica was a winner. And she's actually a double winner, if I understand well, because when I mentioned her as a winner, that was a winner of our Czech competition of PhD students to present a poster at the annual conference of Clarin. And she won that competition and presented her poster. But today I have learned that we will listen to a paper of winners of another competition, this time in the improvement, or I don't know how to call it, of the UDPipe tool, and several questions connected with it. So I'm looking forward to your talk. Please, the floor is yours.
Both mics. Thank you. Can you hear me? I hope so. Yes. So hi, my name is Jana Straková. This is Federica Gamba. We're going to present a talk about our entry into shared task called EvaLatin. The talk is named Towards UDPipe 3 in Science from the LatinPipe, winning submission to EvaLatin 2024. And it's a joint work of 3 authors. The first author here is Milan Straka, who is actually at this precise moment teaching a deep learning course. So he cannot be here. So it's the 2 of us speaking today. I will just present a short motivation why we participated in this shared task. I guess I don't have to introduce UDPipe too deeply in this audience, so I will just devote 1 slide to it. UDPipe or UDPipe 2 is a segmentation, tokenization, lemmatization, and part of speech tagging and morphological analysis, and a dependency parsing tool. The second version was launched in 2018, and we currently have 131 models for 72 languages of universal dependencies of the version 2.12. We have a web service for which we served in a span of 1 year between October the 1st and September the 9th. We served nearly 36 million of user requests, which amounted to 660 gigabytes of text. But UDPipe 2 is quite ancient, the architecture. So we learned that there was an opportunity again, that EvaLatin is an evaluation campaign totally devoted to the evaluation of NLP tools for Latin specifically. And we actually participated in this shared task several years ago. But it wasn't a dependency parsing. At that time, it was a lemmatization and tagging task, but UDPipe does all these things. So we took part, and it was a good entry. This year, this edition, 2024, featured or focused on dependency parsing for Latin. And since it was based on universal dependencies, we thought this would be a good opportunity to try and to implement and evaluate a new architecture for something that could later become UDPipe 3 if it goes well. We called this entry LatinPipe because we just like names with something pipe in it. And now we can start describing the shared task, specifically the data that we had. So at this point, I'm going to give the floor to Federica, who is the expert for Latin data.
Okay, so let's now have a look at the data we've been dealing with for the shared task. Since no specific training data was provided, I'm going to start with test data. For test data, we got 2 works by 2 classical authors, one representing poetry and the other one representing prose. So as for poetry, the text used for test data was Hercules Furens by Seneca, which is a tragedy. And for prose, Germania by Tacitus, which is a historical and ethnographic treatise. You can see in this small table the sizes of the 2 texts, which have both been composed in the 1st century. And that's actually a bit surprising because the official and original guidelines were announcing texts from different time periods so as to somehow deal with Latin variability over time. And at the end, we ended up with 2 texts composed in the same century, but at least they represented different genres. And well, not surprisingly, the test data came as Connell format, but the fields for head and April were emptied, filled in with underscore because we had to predict those. So a closer look at those texts. The prose one, Germania, is actually a very standard variety of Latin, quite plain from the point of view of syntax. Nothing surprising, nothing really hard to deal with. In the Latin treebanks available now in UD, there are some works that somehow are comparable with this text, and they are in Perseus. In the Perseus treebank, we actually have a work by the same author. It's a different work, but the style is very similar because it's another historical treatise. On the other hand, with the tragedy, things are a bit more complicated because since it's a tragedy, the author had to obey to metric constraints. So this means that the word order is somehow artificial. And this also means that since it's less linear, it's way less projective, like the sentence structure. In the Latin treebanks in UD, we have some poetry, but less comparable than what we had for prose. But overall, test data were not really surprising. Like, as I said, they were quite standard. And I'm saying this because, for example, in the previous edition of EvaLatin 2022, one of the test data, one of the texts selected as test data for the cross-time subtask was actually a grammatical treatise from the 15th century, quite bizarre, and with a lot of Greek in it. In this case, no, Tacitus and Seneca are 2 of the most well-known authors from classical times, so more standard, let's say. What is interesting about data is that there is no punctuation in both files, and I need you to keep this in mind because it will be useful later. As for the metrics, the shared task was evaluated with respect to LAS, labeled attachment score, so number of tokens that are assigned, percentage of tokens that are assigned both the correct head and the correct April. And also CLAS, which is the same, but for content words. So function words and punctuation are excluded. In this table, you can see the baseline that was provided by the organizers, and that was obtained by running the UDPipe 2 model trained on Perseus treebank on test data. Why this baseline? Because the UDPipe model was available on the web interface of UDPipe. If we have a look at the numbers, you see that they are pretty low. Like, these scores are surprisingly low. Luckily, ours were not that low. Okay, so that was it for test data. We can now move to training data. As I said, no specific training data was released, but of course, since it's a dependency parsing task, the most natural idea is to leverage UD treebanks. For Latin, we have 5 treebanks in UD, which is quite a nice number because it's high, and especially high given that it's an ancient language. I'm gonna quickly present you what those treebanks are so that you can get an idea of how different the data included is. So first we have the Index Thomisticus treebank, ITTB, which is philosophical medieval Latin dating back to 13th century. And this is our largest treebank. Then we have the LLCT, late Latin Charter treebank, which is again medieval Latin, but earlier medieval Latin, 8th, 9th centuries. And it's a very peculiar treebank because it encompasses charters, so documentary journals, but written in Tuscany, Italy, when Italian was already emerging. So it's clear if we have a look at the data that for example, the declension system is slowly fading away. Then in Perseus, we have classical works, both poetry and prose. In Proyal, again, more classical works, plus the Latin translation of the Bible, the New Testament specifically. And finally, Dante's literary works by Dante Alighieri that was already composing in Old Italian, but he also had a literary production in Latin. It's again medieval Latin, but late, 14th century. And those are the sizes. As I said, ITTB is the largest, Perseus is the smallest. I'm just going to point you out this row, the Proyal row. You can see that there are two sets of numbers. The reason for that is that those are the sizes of the current version, 2.13. But we also exploited a version of Proyal that stems from the 2.10 version. It's going to be clear in a while why, but yes, that's why the double numbers. It's not a big difference anyway. Okay, so we already have a lot of data. We are happy, it's good news, but we have even more. We have this additional treebank annotated according to the UD framework, which is built on the work by Sabellicus, De Latine Lingue Reparazione, 15th century, so Renaissance. This is actually the text I mentioned before when I was talking about the test data for EvaLatin 2022. The grammatical treatise, quite tortuous. That's it. So in this treebank, sentences are quite long, quite complicated, and sometimes they also include Greek expressions. As for the size, it's almost 250 sentences. And we are even happier because we have also Archimedes Latinus, which is UD-like treebank built on a Latin translation of a work, Greek work by Archimedes. So it's mathematics. In this case, this treebank is even smaller. It's more or less 80 sentences. Okay, so we have a lot of data, definitely. But now the natural question is how consistently annotated this data is. And you may partially know the answer because this is something I already presented during the PhD seminar. We observed these treebanks to be not really consistent. And that's why we carried out a harmonization process that was composed of two phases. First, we focused mostly on syntax and then only on morphological features. The whole harmonization process was modeled on UDante version 2.10, and that's why I mentioned size 2.10, version 2.10 before in the size table. And why UDante? Because it's the only treebank that is native, UD native, and not converted from any other annotation format. Because it's the newest one, so hopefully it follows the latest version of the UD guidelines. And because the team behind UDante is the team responsible for UD guidelines for Latin. Back then, when we carried out this harmonization process, which was 1 year and a half ago, Perseus and Proyal had the status of neglected treebanks, neglected in the technical sense of the UD infrastructure. So meaning that 3 years had passed since the old evaluation error. Quickly, a couple of examples. You have on the left the pre-harmonization tree, and on the right, the harmonized one. So in this case, we are working with comparative clauses, and well, it's an elliptical comparative clause, quam vestimentum, more than raiment. And originally, vestimentum was annotated as the subject of an adverb, and the adverb was just an adverb, which is not really correct. So we modified the tree, and now it looks like this. So what was an adverb is now a subordinate conjunction and is properly attached as a mark to what is the head of the comparative clause. Last example. Before the harmonization, there were issues with copular constructions. So mostly in ITTB and LLCT, probably due to conversion errors, meaning that the copula was the head of the clause, and it's not supposed to be. So we took care of this, and now it looks good. So these two tables, we are not going to read all the numbers, don't worry. But it's just to tell you that this harmonization had an impact on parsing. With small tree banks, we were able to reach a plus 17% improvement. So it's just to show you that it matters and it affects performances. And that's it for harmonization. End of the summary. Now the question is, what happened after? Like, we released a set of harmonized tree banks. Are those tree banks just sitting there in my GitHub repository and nobody cared about them? Luckily not. So starting from ITTB, LLCT, and Udante, they are all maintained by the same team in Milan, Italy. And we started a close collaboration with them so that they finally ended up releasing a harmonized version of those tree banks. With Perseus, it was even simpler because nobody was actively maintaining the tree bank. So we were able to release in the UD official release, the harmonized version right away. And now I'm maintaining it, so hopefully it's still harmonized. With Broil, things were a bit trickier because the Broil team was not really eager for harmonization. And the reason for that is that they have many tree banks for ancient languages. Besides Latin, they have ancient Greek, Gothic, and Old Church Slavonic. So they didn't want those tree banks to diverge from the original common annotation schema. So what did they do? They implemented some changes, but they didn't say what. Which results in the fact that now we know that we have ITTB, LLCT, Udante plus Perseus being fully harmonized. And with Broil, we don't really know. If we go and have a look at the official UD GitHub repository, there's a bunch of commits where the only commit message is update. So it's very hard to track down what was changed. And how does this relate to the shared task? To train our model, we needed to know whether it was better to train on the officially released Broil or on the harmonized version. We didn't know how to find out, if not by trying and experimenting with it. This harmonization thing really matters because the shared task was organized by the same people behind ITTB, LLCT, and Udante. So we expected test data to be more or less annotated in the same style of those tree banks. And what about the small tree banks? Sabellicus, once again, annotated and maintained by the same team, was already consistent enough, but was even harmonized again before being released 2 months ago. And Archimedes Latinus is consistent enough because it was an independent project, but annotated under the supervision of the people in Milan. It was before the harmonization because it was annotated in 2021, but still, it was good enough. So a couple of examples about Broil. This is something that has been changed. By looking at the data, it was clear that they dealt with this problem. And the problem concerns adverbial clauses. We have poste aquam agros homines feria damassent, which means after that this wild man had become enamored of the lands. So adamassent is the head of the clause, of the adverbial clause, and it's supposed to be their head. However, here it's annotated as fixed and attached to quam, which is actually the mark of the clause. But now in Broil, this tree looks fine. However, there are still issues and constructions that haven't been dealt with. For example, numerals. On the left, you have the current tree in Broil, and on the right, you have a zoomed in tree of how it's supposed to look like. So in a case like Viginti quatuor, 24, 4, quatuor is supposed to be attached as flat to the first number. And then the whole thing modifies as nummod, whatever it is modifying. That doesn't happen. So we still have some problems in the original Broil. Okay, so now the question is, in light of that, how much does Royal matter? We don't know. We will find out after the method.
Thank you for covering the data section. I will now speak about the methods. And as I cover the technical part of the shared task, 20 minutes later, these two paths, the data and the methods, will converge into a nice joint result of the shared task, which I personally found very joyous, cooperating with the linguistics and the work that was done on the harmonization part. So now the methods. The parser, the LatinPipe, is very, just like UDPipe 2, is a graph-based dependency parser. That means that the tokens of the sentence are represented as graph vertices. Each token gets one vertex in the graph. And for each pair of the tokens, you will have a graph edge. And on these edges, for each token pair, you will get a score that says how probable is it that these two words should be related in the dependency in the dependency tree. And once you have these scores for each pair of the tokens, you can run a very deterministic algorithm, graph algorithm, that will find the optimal spanning tree or arborescence if there is not just one root. It's called Edmonds algorithm. I am not covering it here, but it's not deep learning, it's just a graph algorithm. So how do we decide what scores to put on the edges? Well, obviously, we can use the deep learning networks to estimate, to score the edges. But just differently to UDPipe 2, we will use a fine-tuned pre-trained language model for scoring the edges. I will now show the pre-trained language model and the very basic and first version of the architecture. That's not very surprising. There's nothing that's very new from the state of the art, but I will slowly go through the picture and explain what's in it, and then we'll add components to it. So the figure is supposed to be read from the bottom to the up. So here we would have inputs, and up there are outputs. The exact input would be a sentence in this example, abit transfratum. So imagine abit transfratum here. It apparently means he crossed the river in Latin. And before the tokens can even enter the bird transformer, they have to be tokenized so that the tokens fit the tokens that the bird expects. So these are different than the tokens that we would have on the linguistic level. So every bird model is always distributed with a tokenizer that corresponds to this bird model. So in this case, the words are split up 8 transfratum. So the first word was split into 2 subwords. In our implementation, we will use always the first subword of the word, and we'll ignore all the other subwords that the words was split into. And this part, the bird part, is the main component, the main computational component, the one that has the transformer, that has the layers in it, that computes everything, that does the contextualization, simply the bird. And on the output of bird, you will have the contextualized word embeddings that would be vectors of real values, of hundreds of them. For the base version, you would have several hundreds of real valued vectors for each word, for each subword. And for the large version, you would have 8,000 values. So this part here, the green part here, is what we call bird, what you know as bird. But obviously, you need to somehow process these contextualized embeddings to transform them into the scores that could go into the graph. And for this, we have the upper part of the figure that is usually called the heads, the purple and pink parts. And these are modules of the neural network that will compute from the contextualized embeddings the probability scores of the tokens belonging together in the dependency tree. And for these scores, for this probability distribution, we would have this dependency scores attention. So we obviously need a scoring head for two words. One would be the head, the other would be the dependent, and then we need to combine them into a dot product attention to get the scores for the graph. And once we have the scores and the graph is fully scored with some predicted values, then we can run the graph algorithm. And once the shape of the tree is determined, then we further need to assign the dependency relations to the edges, and that we can do with another classification head. That's just a simple classification head, no dot product attention, and that assigns dependency relations, deprels, to the edges. So this is a very basic overview, nothing new. This is not, there are no tricks in this. Now I will go to the first experiment. So now the question is, what kind of bird? You know, there are so many birds like bird, Roberta, whatever, XML, Roberta large, base, and so on. So we tried a few, we tried many, but I will show you the 3 of them, which we tried. So our first try was Laberta, which is monolingual bird. That means it only has seen Latin during its pre-training. Then we tried Filberta, that's also a monolingual model that has only seen Latin during its pre-training. And then we tried XML Roberta large, that's a multilingual model. And as you can see across the board, these are the UD 213 that data tree banks. This is the macro average. That means averaged along the tree banks, and it's measured on, these experiments were done before we entered the testing phase. So these are preliminary experiments. You can see that going from base, even though it was a monolingual specifically trained Latin model, to multilingual but large model is beneficial. So the moral of the story here is multilingual large is better than monolingual base. So capacity is better than specificity. Okay. Yeah, there was a figure here and it's not now. Okay. Yeah, we lost the figure. We cannot do anything, right? There's yeah, it's not. No, yeah, no, it's already, never mind. I can describe the figure by, so you see there is a free space here, right? And what was going to be on this free space is obviously we have several birds. One of them is Laberta, the other was Filberta, and then we have XML large. So there is no obstacle in trying to concatenate these models. So we would have here another model that was in yellow color, XML large, that actually splits the tokens in a different tokenization because it's a different model. It was, I think it was Abit, trans, and Fretum got split into 2 subwords. So we had a different tokenization here. And then these, we get the same word embeddings, but they can get concatenated. That means they are appended. So we would have another addition of contextualized word embeddings from a different model. So we concatenate the models and we concatenate their outputs precisely. So this is where the figure should have been. And now you have already seen the upper part of the figure of the table. The new results are the bottom section of the table. And what you can see here, that's also not very surprising, that you can see that adding capacity, concatenating pre-trained language models, again, helps across the board and in average too. So it is beneficial. We ended up submitting this monstrosity to the shared task. Will obviously probably not serve such a thing or in deployment. That would be too expensive. What I want to say, this is also not very new idea. Current named entity recognition actually combines several, I think 11 pre-trained language models. And unlike us who just blindly, naively tried several combinations, they choose which pre-trained language models to use by reinforcement learning. So that's something to read if you're interested in. Now some interesting incremental improvements to the architecture. If you remember the figure, there was the green part, that was the bird, and then the purple part, these were the heads. And what you can do is completely freeze the weights of the pre-trained language model, the green part, and not update the weights in them. So there is no stochastic gradient descent, no training done on them. They are not trainable. Trainable is false in Keras. And you train the other parts of the pipeline, of the architecture. And if you do that before you start fine-tuning, that helps the model to start training from a good place. It really helped a lot. We were very surprised. We did frozen pre-training for 10 epochs, and it gave us 1.5 point in last score for basically no cost. I mean, no cost in capacity, in GPU memory, nothing, just 10 frozen pre-training epochs. So this is common practice in vision when they do this in a much more sophisticated schemes than we did, but it gave us some improvements. Yay, we have figures. That's so nice. So now you can see here what I was speaking about when I was concatenating the models. These are the concatenated word embeddings. And this is a game of find two differences. The left side is before the incremental improvement, but actually the heading is giving us the answers. So, and on the right-hand side, we added two bidirectional LSTMs on top of the contextualized embeddings. This might seem like we are going back in time in history, like why would anyone do that? Because Hochreiter and Schmidt-Herbel already have done that all right. So yeah, it does help a little bit. I would say marginally. So when we add two bidirectional LSTM layers on top of already fine-tuned transformer models, it does help in average, and it did help in the shared task. Now the answer for that, why that is happening, is a little bit more technical, but we think it's because LSTMs look at the contextualization a different way than a transformer with positional embedding does. And namely, it does so in a relative, very local way that actually is preferred or favorable to dependency parsing task. Anyway, we will need LSTMs for the next step. So the next step is, if the shared this particular shared task, which was in dependency parsing, provided us with gold part of speech tags. And if you have some gold data that are allowed to be used, why not append them to the contextualized embeddings that you already have? That's for free. If it's allowed, that's good. So we did it, and no surprise here. If you have available gold data on the input and you can use them in a shared task, then you should do it. Obviously, in real life, we'll not have any gold data. We'll just have to go from raw text without help from UPOS. You post is part of speech tags in dependency in universal dependencies. So now we are nearing to the data. So we have seen that Latin people have been quite busy annotating tree banks, and so now we have 5 universal dependencies tree banks and 2 more that are not included in the official universal dependencies releases. And what we can do, we can either train each one and single data set on its own and have them evaluated on its own, or we could do some kind of joint training on all the data that we have available. This cannot be done it can be done in a naive fashion when you would just get the data, somehow concatenate the files and read from them, but that's a naive approach that will not get the best results. Good results in multi-treebank training are achieved if you sample cleverly according to a parameterized probability distribution. When done this, you can train on multiple tree banks, and we got improvements on macro average. Now, on this particular task, it seems that in Latin, the small tree banks, that's usually across all tasks, the small tree banks benefit the most. The medium-sized tree banks are so indecisive, and the big tree banks on some tasks, I'm not speaking about Latin, but on other tasks too, sometimes tend to decrease a little bit, but overall it's a gain in macro average. And besides that, handling just one model is very practical, both for the shared task and for deployment, when you don't have to handle 131 models and maybe and rotate them in memory. You can just have one model. So I'm now going to sidestep from the shared task and show you some results from another shared task where we did multi-treebank training too. This was the coreference resolution shared task from last year and the year before. And in 2022, we actually focused on multi-treebank models, and the paper was specifically called Effectivity of Multilingual Models for Coreference Resolution. And please ignore most of the numbers. I just took the table from the paper, but what I want to show here is the first line is the baseline. These are the absolute numbers. So it's the shared task submission on XML, Roberta base individually trained on each one and single of the data sets. And these are some numbers that we achieved with that. The last 4 lines is what is interesting to us. So this first line, the 4th from the end, is when you go from a base model, Roberta, multilingual, to large model, and you see that's also not surprising that you have some nice gains just for increasing capacity. But now why this slide is here, let's go from training large Roberta multilingual individually to multilingual training. And by multilingual, I mean all these data sets sampled into training data according to nice probability distribution. And you see these are increments relative to the baseline. So you need to detract it. So you get +2 points on average, but you get plus points across the board. So this is different observation from the Latin dependency parsing. We didn't observe any of the tree banks going down. All of them benefited. And the same effect is in these 2 pairs, Rembert individually trained and Rembert in a multilingual setting, where you would train in multi-treebank setting. Again, similar numbers from 2023. Now, this is a different view. So this is the final submission, single multilingual model. That means it's a model that was trained on all the corpora together in a multi-treebank setting. And the second line of the table is what you will lose if you train these models in a single treebank setting. So again, it's quite a loss. So back to dependency training shared task. The final trick for the shared task is ensembling. Ensembling is when you have several models, each one of them is initialized randomly, independently. They have different starting weights and they all converge to a slightly different place. And then you take their outputs and the outputs get somehow ensembled, mostly averaged. So this would be one model result, and this would be 7 models averaged. And again, we got a nice improvement almost for free. So this would be the final trick that we did. So to sum up the architecture, it's a lot of tricks, and this is how it looks in the end. The bird, the concatenation, the addition of the gold part of speech text on the input, 2 bidirectional LSTMs, and the heads that somehow compute the final distribution from the contextualized embeddings. What I have not been speaking about and what's new on this figure are these blue heads. These are just very simple classification heads for part of speech text and features, morphological features, because these were not required by the shared task, but we wanted this to eventually be UDPipe 3, so we actually coded this part too. And if time is left, I can show you some results on morphological part too. This is a complete architecture. Yes, why I'm showing you this, this is a comparison with the previous work. The bottom section of the table is previous work. And this is the situation we were in before we went into the testing period of the shared task. We knew that our results surpassed known state-of-the-art on Latin dependency parsing, so we were quite ready for the shared task. So the best numbers are found in the ensembles section, but for a very fair comparison, one should probably compare with the non-ensemble section where there is just one model, because I think the previous work is also reported on non-ensembled numbers. And now we will see the results of the EvaLatin shared task.
Okay, so if you remember, we concluded the part about the data with a question. How important is Proyal given this fabulous architecture that we have just seen? Does it really make a difference? It's not the only tree bank we have, and it's not the largest. I'm gonna give you an answer with numbers. If we focus on the upper part of the table, you have results with the multi-treebank training with different Proyal versions. And you can see in bold that all the best results are obtained when harmonized Proyal is employed. But the lower part of the table makes it even clearer. So in the blue rectangle, we have our final submission, well, one of the two. It's ÚFAL LatinPipe submission 1. And you can see that once again, using harmonized Proyal leads to better results than using either original Proyal or no Proyal at all. In green, you have the improvements. It's more or less 3 points. So we can extract three take-home messages from this table. The first one is that using harmonized prior is the best solution, better than original prior and better than no prior at all. The second one is that using original prior is still better than not using any prior at all. And we will see why. And the third one is that those small tree banks, so Sabellicus and Archimedes, when testing on the UD 2.13 tree banks, didn't really help because, of course, they're very small, their size is very limited. But it is, in this case, they helped a bit. But going back to prior, why is prior so important? Why does it make such a difference? Because if you remember, I told you that test data has no punctuation. And prior, among all the 7 tree banks that we have, is the only one without punctuation. So some of the models, the model prefers that based on statistical clues and decides that test data is more similar to prior, or the other way around. Prior is the most similar tree banks among those that we have. So for this reason, we really need prior to be consistent with the data. Otherwise, we would predict the divergent annotation. A closer look at the harmonization effect. In this case, we are training within the single tree bank scenario setting. And you can see once again that harmonized prior helps quite a lot. It's around 5% over original prior. And that in general, you see that the best results are obtained with prior. So that's yet another proof. One example, this is a predicted tree. Actually, it's the first sentence of the prose text. And you have here the annotation predicted when the model is trained with harmonized prior, which is in blue, and in red, the annotation predicted with original prior. So where do we see differences? Mostly in coordination. So if, as you can see here, we have this phrase, a gallis retisque, which means from the goals and rations. We have que, and the coordinate conjunction, which is attached to the preceding conjunct, but correctly here in this case, by harmonized prior, well, model trained on harmonized prior. But when the model is trained on original prior, the officially released one, the conjunction is attached to the first conjunct. And the reason for that is that before being harmonized, coordinations in prior were still treated according to version 1 of the guidelines. Then they modified this. It was one of the changes they applied, but probably not consistently because the model still learns it in the wrong way most often. And you have another example here, Reno et Danubio, by the Rhine and Danube. In blue, you see that the second conjunct is correctly attached to the first one, but with normal original prior, it is attached to like a word that doesn't belong at all in the phrase. And with this, I conclude, and Jana will tell you about this punctuation issue that we had.
Yes, thanks. So as you see, we had a lot of trouble with the prior tree bank. We really did. So we were allowed to submit 2 submissions. The first one was with harmonized prior. We knew that would work well. And the second one, we battled and we decided to submit something that is trained without the prior altogether. But the prior is the only part of the training data that has no punctuation in it. All the other training data do have punctuation, but the shared task data, the test data have no punctuation. And when we realized this, we realized bad things may happen. And how bad is it? Well, pretty bad. It turns out that 56% of last sentence tokens in test data are mistakenly recognized as punctuation, although the test data have obviously no punctuation, and these were in fact very common and regular words with meaning. And worse yet, there were no dependency relations attributed to them, because who would attribute any dependency relation to punctuation, right? So the statistical clue about the last token in the sentence in the training data being the punctuation was so strong that the model never learned how the word should look, that it's always a period, a full stop, and never a verb or a noun. It's just the last word, and the statistic says it all. But now, when you get a new test data without punctuation, the model experiences a domain shift. So what it does, it generalizes over the words and fails from our perspective. So it does a generalization, but it is not the generalization that we wanted to see. And why I am saying this is it illustrates my point that the deep learning methods understand the data well, but they don't understand the world that it is describing so well. So they learned that the last word is punctuation, but no human annotator in their right mind would annotate the data in such a way. So what can we do? This was already well into the tested period. So we didn't have so much time when we learned this. So there would be a correct fix, retrain the models on training data with punctuation removed, but we don't have time for that. Training takes time. So what we can do, we can change the test data. We can append dummy punctuation at the end of the test sentences, have the model attribute punctuations to these dummy punctuation, remove the punctuation again, and then submit this. Well, this is what would happen if we chose to ignore the test train data punctuation mismatch. We would just like that lose 5 points in loss. And that's quite sad. That's the second reason I'm showing this issue with punctuations. You can do nice tricks with architecture and adding layers left and right. But if you don't check for punctuation in test data, you can lose 5 points just like that, you know, on a stupid thing. This was our second submission to the share task. And to sum up, where we are on the road towards UDPipe. This is for fun. A comparison on the left. I have a weird sense of fun. I know. On the left side, we have the UDPipe 2 architecture, and on the right side, we have the UDPipe 3 architecture. The first thing illustrates how visualization of architectures moved in 6 years from something that looks like UML diagram, I don't know, and colorful to something that looks like a unicorn. Interestingly, we moved from recurrent neural networks to this is the important part, to fine-tuned pre-trained language models. Where we are with UDPipe 3, what's done? Part of speech tagging is done, morphological analysis is done, dependency parsing is done and tested in the share task. What is missing? Lemmatization, that's a lot of coding of characters, edit distance, indexes and such. But the remaining research question is, will the trick with multi-treebank model, just one to rule them all, work for 131 UD data sets? Can we serve just one model for all the languages or not? So this is something that's waiting for us in the next few weeks, months. Takeaways or lessons learned. Multilingual large model is better than monolingual based, as I said, capacity over specificity. Concatenation, if you can afford it, is better than a single language model. That's actually also a question of capacity to a degree. A frozen pre-training is a performance boost for almost free. Multi-treebank training helps on macro average, plus it's very handy. Ensembling is important in shared tasks. You can get 3 points for that. Last but not least, something for linguists, annotation style harmonization helps learning. And that does not mean that the formats are the same, but the annotation style is unified. I believe that's all. So that's all from the two of us, and we're ready for questions.